a geometric series is when you start with a initial value. Let's try to spell that right. Initial value. And you get subsequent values that are all that initial value times a common ratio. So to get the next value, you multiply the first value times this ratio. To get the value after that, we multiply that previous times that ratio again. So we're always multiplying by this common ratio here, and so on and so forth. And so if we keep multiplying by that common ratio, we get these these future terms. And so what we have then is a really special type of series where we have a known equation to find a sum of that series, as long as we know the initial value and value of that ratio. If we take a look at what happens when our ratios are certain values, we can kind of get an idea of convergence and divergence and things of that matter. If we take a look at just this first one here, the initial value being 3 and the common ratio of 1/2, then if we write out the series here, the series will look something like this. We have an initial value of 3, we have a common ratio of 1/2 to the n power. We start at n equals 0. And the reason why we start this particular type of series at n equals 0 is because this first term has been multiplied by that common ratio 0 times. And so that's why these series start at 0. And so when we take a look at this, the first term is 3 times 1/2 to the 0, which is 3, and then 3 times 1/2, which is 3/2, and then 3 times 1/4, which is 3/4, and then 3 times 1/8, which is 3/8. And so if we look at this, we can see that these values get smaller and smaller and smaller, and this common ratio, this 1/2, is the thing that's making that smaller and smaller. Likewise, if we take a look at just making the common ratio a negative value, then we're looking at 3 times negative 1/2 to the 0 power. So it still starts at 3, it's the initial value. 3 times negative 1/2 is going to be adding a negative 3/2. And then when we square this 1/2, we're going to get a positive 1/4, so we're going to be adding 3/4. And as we take 1/2 to the 3rd power, that's going to be negative 1/8, so it's going to be subtracting 3 times 1/8, or 3/1/8. And so we can see that when r is negative, we start to get this switching of the signs from positive to negative to positive to negative to positive. And so if we're going to be all adding here, and if we're going to be a combination of adding and subtracting here, this sum is going to be a different value. So if we evaluate these sums, our a value is 3, 1 minus 1/2. So that's 3 divided by 1/2. For when r equals 1/2, the sum is 6. If we look at the sum here, then it's 3/1 minus a negative 1/2. Minus a negative is a positive. So we have 3/3 3/2, which ends up being 3 times 2/3 ends up being 2. So we have a much smaller sum here, which kind of stands to reason because we've done some subtracting here that we have not done here. So we end up with a larger sum here and a smaller sum here. If we take a look at then this geometric series, and we have an initial term of 3. We have our r now of 3/2. And so if we write out the sums in this, start writing a sum in this series, we start at 3, and then we add to it 3 times 3/2, which is 9/2, which is 4.5. And then we have 3 times 9/4, which is 27/4, which is something that's slightly larger than 6. And we have 3 times this to the 4th power. So this to the 4th power is going to be this to the 3rd power. This to the 3rd power is going to be 27 times 3 is going to be 81, and 2 to the 3rd power is going to be 8. And this is something slightly bigger than 10. So as you can see, these terms themselves are getting bigger with each successive term. So this is going to end up having a sum of infinity because we're adding bigger and bigger numbers with each term we add. And so where does this switch off from being a finite value to being an infinite value? And for that, we're going to have to look at a common multiple of 1. And so if we look at that common multiple of 1, we look at the fact that that's just saying 3, and then 1 squared is still 1, and 1 cubed is still 1, and 1 to the 4th is still 1. Okay, so if we perpetually add 3 to our sum, we're still going to have an infinite sum. Okay, so anytime, even if we have an r of equal to 1, we're still going to eventually add up to infinity. So as we approach a common ratio of 1, we're going to have subsequently smaller values. As we go past that value of 1, we're going to have subsequently larger values. So that's why when we look at the definition of what converges and what diverges, the geometric series will tell you that as long as we are between -1 and 1, we're going to have convergence here. And if we have a common ratio that is outside of that range, so bigger than 1 or smaller than -1, so bigger than or equal to 1 or smaller than or equal to -1, we're going to have divergence. And so this test can be used to determine either convergence or divergence, depending upon what you're being asked to find. If you're being asked to find a sum, then the sum is found by just calculating that value particularly. So for geometric series, it says verify that the finite series converges. All we have to do is look at the value for r. So we look up here. We verify that the series begins at 0. That's important for finding its sum. We identify that the value of a is 2, and we can identify that the value of r is minus 1/2. So we know that r is minus 1/2. We know that that is less than or equal to, I take that back. We know that r equals minus 1/2, and we know that the criteria is the absolute value of r being less than or equal to 1. So we know that what that means is that r must be trapped between -1 and 1, and it is. So we know that this series 2 times 1/2 to the n converges. And when we make a determination that it converges, we have to state the test by the geometric series test, and GST is good enough, but we do have to state the test and make sure the criteria is really plainly stated there, that r is 1/2 and it's between those two values. To find its sum, and I've been calling it S sub infinity, but really we can call it S sub n as well. To find that sum, then we can just substitute the values into that equation for the sum. And that's why I said it's important to note that this has to be set at 0 in order to find a sum. We have to know that we're dealing with the first term being 2, and then subsequent terms being multiplied by -1/2. So the first term is 2, and r is -1/2, so that looks like 2 over 3/2, 1 plus 1/2, which is 2 times 2 over 3, so the sum here is 4/3. For this series, again, it's the same instructions. So we're going to have to determine convergence or divergence. We have to determine convergence or divergence, and we're going to have to find the sum if possible. So again, we make a quick check here. We have a starting point of 0. That's important for the sum. We can acknowledge that our a is 2, and our r is 5/4. And so we, again, make it a very clear statement that r is 5/4. For divergence, the absolute value of r has got to be greater than or equal to 1. And it is, it's 5/4. So we know that this series then of 2 times 5/4 to the n diverges because of the geometric series test, which means then we can't really find the sum. We can't calculate anything. We know the sum is infinity, but we don't really calculate it. In fact, what we just say is the sum does not exist because it's not a finite value. In this example, again, the same instructions. We're looking for either a statement of convergence or divergence, and if it converges, find the sum. A bit problematic here. We need this to start at 0. And so in order to, the easiest way to do that is just to write out the first terms, the first 2 or 3 terms, and then rewrite this expression. So this starts at 2. And so what we're looking at here is this first value that goes in here is 2. So the first value then is 1/4 to the 2, the second power. The next one is 1/4 to the third. The next one is 1/4 to the fourth. The next one is 1/4 to the fifth. And so if we look at that, we'll just write out these first couple of terms. That's 1/16. That's 1/64. That is 1 over, what is that, 256, I believe. Let me just check that real quickly with a calculator. Um, 64 times 4. Yep, 256. And this last term here is 256 times 4. It's 1024. So 1 over 1024. Okay, so there are the first 4 terms of the sequence. Now we can go ahead and rewrite this with n equal to 0. So we have our first term here. There's our a. We know that when we go from this term to that term, we multiply by 1/4. So there's our r. So we can rewrite this as 1 over 16 times 1/4 to the n. And that's the same as saying this 1/4 with the 4 just to the n, and this are equivalent expressions. So now we have our a. Now we have our r. And now we have our appropriate starting point to find the sum, if in fact this converges. So we look at the value for r here. R is 1/4. And the condition for convergence is that we need the absolute value of r less than or equal to 1. That means that r needs to be trapped between -1 and 1, and it is. So the series of 1/4 to the n, starting at 2 to infinity, converges because of the geometric series test. And we can find the sum now, but to find the sum, we need to take this information. So we have an a of 1/16 and an r of 1/4. So the sum is 1/16 over 3/4, which is the same as 1/16 times 4/3, which is 1/12. So the sum goes to 1/12. Okay, if you notice for this one, again, the same instructions as before. So whether or not it converges, find the sum if it does. We are set up to appropriately find the sum if we need to. We have an a of 2. We have an r of -2/3. So if we have an r of -2/3 and we know we converge if the absolute value of r is less than or equal to 1. So that means it's trapped between -1 and 1. This is trapped between -1 and 1. So the series 2 times -2/3 to the n converges because of the geometric series test. And now we can go ahead and find the sum. Our a value is 2. The r value is -2/3. So that's the same as 2 over 1 plus 2/3. That's 5/3, so that's 2 over 5/3, which is the same as 2 times 3 over 5. So we're looking at 6 over 5 for the sum. Sometimes what they'll do here is they'll give you a partial expression for the sum. So they give you the first 4 terms of this series. And so they expect you to be able to come up with the expression in sigma notation. And so we're looking at that basic form of the first term, that'd be the a sub 1 term, and then the common ratio. And so the first term is right here. You just find it at the beginning. Okay, no more difficult than that. And then we have to look at that common ratio. So what do we multiply 8 by to get 6? Well, 6 is littler than 8, so we know we multiply it by a fraction. What fraction? Not quite sure. So I'm going to go here and look at this one because we know the ratio has to be the same. What do we multiply 6 by to get 9/2? Yeah, I'm still not seeing it. So I'm going to come here and say, well, what did we multiply 9/2 by to get 27 over 8? And now at least I can say, hey, I've got 2 fractions here. I can go from 2 to 8 by multiplying by 4 on the bottom, and I can go from 9 to 27 by multiplying by 3 on the top. And then I can kind of work backwards. Does that work to get from here to here? Now let's see, 6 times 3 is 18. 18 over 4 is 9/2. So yep, that works. Does it work going from 8 to 6? 3 times 8 is 24, divided by 4 is 6. So yep, this is definitely the common ratio. So writing this, if this is called a sub 1, it is by definition the 0th term. In other words, we haven't multiplied 8 by 3/4 at all to get that first term. So the first term is 8. The common ratio is 3/4 to the n. Now we can go ahead and determine whether or not we have convergence or divergence. So we know we have an R of 3/4. We know that converges since the absolute value of R is less than or equal to 1. So again, we have that R being trapped between -1 and 1, and it is. And so we can go ahead and find the sum. And so our sum then, our A is 8, our common ratio is 3/4. So we have 8 over 1/4, which is the same as 8 times 4 over 1, which is 32. So the sum of this infinite series is 32. For this example, we have a repeating decimal, and a repeating decimal is really the sum of an infinite series. So if we think about a repeating decimal, we know that the bar over the 8 and 1 means the 8 and 1 repeat. And so if we look at this portion, that's really 81 over 100th. And if we look at this next repeating portion, that is really 0.0081. So that's really 81 over 1, 2, 3, 4 over 10,000. And if we look at the next repeating decimal, that's really 0.000081. And that's really 81 over 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. That's really 81 over 1 million. And so we can take these then and say, well, we can get 0.8181 repeating if we take 81 over 100. That would give us a 0.81, and we add to it 81 over 10,000, because that would give us a 0.0081, and we add to that 81 over a million, and so on and so forth. We can get the next set of 8 ones, and the next set of 8 ones, and the next set of 8 ones. So if we look at that, then we can say, well, that's really this first term here is really my a sub 1, and what do I have to multiply by to get from here to here? Well, the top doesn't change at all. So we know that our common ratio, then the top stays at 81. So we know to get from 81 to 81, we multiply by 1. To get from 100 to 10,000, we multiply by 100. So our common ratio then is 100. So we can write this repeating decimal. We can write that repeating decimal as the sum of 81 over 100 times the common ratio 1 over 100 to the n power. So there's our common ratio. Now we can say, does this converge and diverge? Now, if we start talking about that kind of stuff, do we need to run tests? And the answer is no. We already know the sum. The sum is 0.81 repeating. So if we already know the sum, it's got to converge, because we already have the sum. And in fact, we could confirm that because our common ratio is trapped between -1 and 1. If we wanted to find a sum just to convince ourselves, we could say, well, A is 81 over 100, and R is 1 minus 100, or R is 100. So we have 81 over 100 divided by, this is 99 over 100. And so that's the same as saying 81 over 100 times 100 over 99. And so the sum is 81 over 99. And if you take 81 divided by 99, 81 divided by 99, you get, let's do that correctly, 81 divided by 99, you get the 0.818181 repeating. So that is the sum of the series. So this is already the sum. Well, if we have a sum, we know it has to converge. The idea is, can we write it in series notation instead of a repeating decimal?